Hey folks, in this video we're going to be talking about atoms, molecules, and moles. What are moles? You'll find out. So, we got a few objectives up in here. I want you all to be able to define the mole and explain its use in chemistry. And just so you know, we're not talking about those little burrowing critters, little burrowing moles. I want you to be able to use Avogadro's number and define it, more so, and then use it in the context of chemistry. I want you to be able to define atomic mass and molar mass and explain their uses in chemistry. And I want you to be able to use the mole roadmap as a tool to assist you in performing conversions between moles, mass, volume, and number of particles. So we'll look at how to do that later. So we got some new vocab up in here like mole, Avogadro's number. We're going to be talking about molar mass, the mole roadmap, and also this concept called standard temperature and pressure. Let's go with all of that. So the mole and Avogadro's number. Well, the mole is a unit that we use, which we abbreviate MOL. I don't know, getting rid of the E's saves a little bit of time. It's worth it. And so we use this unit because atoms are too small to count individually. They're so tiny that we cannot visualize them with traditional forms of microscopes. And so the mole is a unit for counting atoms, or molecules, or formula units, or other things that are very tiny. Now, this is kind of like how bakers use the term a dozen to measure baked goods, because bakers, when they're making and selling baked goods, they've got a lot of them. It's easier just to say, hey, we're going to sell 3 dozen than it is to say we're going to sell 36, cuts down on math, and makes things easier by using smaller, simpler numbers. Well, a dozen is equal to 12. A mole is equal to Avogadro's number. And now you're going to ask, well, what is Avogadro's number? Let's talk about that. Avogadro's number is this gigantic number. It's 6.022 times 10 to the 23rd. So there are 23 digits behind this 6 between that and the decimal point if you were going to write that out in standard notation. That is a gigantic number. And so this is how many of whatever particle is in 1 mole. So if I'm talking about 1 mole of gold, I know that that's going to contain 6.022 times 10 to the 23rd gold particles, or gold atoms. If I'm talking about an ionic thing, like sodium chloride, I know 1 mole of sodium chloride is going to contain 6.022 times 10 to the 23rd sodium chloride formula units, or NaCl's, combined together. So 1 mole of any chemical is going to have 6.022 times 10 to the 23rd particles of that chemical, the smallest particles. If we're talking about glucose, C6H12O6, well, this is a covalent compound that is made up of molecules, so 1 mole of glucose is going to contain 6.022 times 10 to the 23rd glucose molecules. So anytime you have 1 mole of something, you have Avogadro's number of that thing. We could also use this for silly stuff, like you could say I have a mole of donuts, but if you actually had a mole of donuts, there would be so many donuts that it would cover the surface of the earth many times over, and it would just be unreasonable. So the mole is usually, we use some as a unit for converting between other units. The mole itself is not usually our starting or stopping point for things. So if we want to figure out what the mass of a sample is, or if we want to convert mass to volume, or if we want to figure out how many atoms there are in a sample, the mole is very useful for helping us convert between these 3 different things. Oh, atoms, you got covered up. So that's fun. Let's talk about those in a little bit further. So if we're using moles, one thing that's very important to know is that the mole relates to the atomic weight of a particular element. So our atomic weights, if you recall, are found on the periodic table with each of our elements, and each element has its own unique atomic weight. And this is going to be, as we discussed previously, based on the natural abundance of the different isotopes of that element that exist in the wild. But what's really important for us to know is that each element has its own unique atomic weight. So the mass in grams of 1 mole of that particular element is equal to that atomic weight. So if I have, for instance, 6.022 times 10 to the 23rd atoms of a particular element, these collection of atoms are going to weigh the same as that atomic weight found on the periodic table. So if I have Avogadro's number of gold atoms, they will all together weigh the same as the mass of gold, the atomic mass that is shown on the periodic table. This is the atomic mass of gold from the periodic table. So atomic weight tells us how much does 1 mole of that element weigh, or what is the mass, particularly, of that 1 mole of element. And so we're always going to express atomic weight in grams per mole, because if I have 1 mole, it tells me how many grams I have. Very cool. So this on itself is useful because we can then use it if we want to talk about compounds, because remember, compounds are made of multiple elements. So the molar mass is what we use to describe a compound. And usually this is particularly used for covalent compounds, but we're going to use it for all compounds and most of the time. So again, this is the same thing as the atomic weight, except instead of for describing a particular element, it describes a particular compound. So it's the mass in grams for 1 mole of a particular compound. And we're going to use the term formula unit mass when we describe ionic compounds, or some folks will. I'm probably just going to use molar mass to describe the mass for 1 mole of any kind of compound. And so if I want to calculate the molar mass for a compound, I'm going to look at the atomic weights for each of the elements in that compound, add up all those atomic weights, and that will give me my molar mass. So we'll look at that more in our next slides. But it's important to note that also molar mass, just like atomic weight, is going to be expressed in units of grams per mole. This tells us how many grams there are in 1 mole of a compound. So let's look at let's look at calculating molar mass. So again, the first thing we want to do is identify the atomic weight of each of the elements that are found in whatever compound formula you're looking at. And then we're going to multiply each of those atomic weights by the corresponding subscripts. If there's parentheses, we have to distribute our subscripts that are outside the parentheses into the parentheses. And then we're just going to add together all the products for these multiplication steps. So let's look at 2 examples. First, we'll look at H2O. And I'll say, all right, hydrogen, I can get that atomic weight off the periodic table. I can get the atomic weight of oxygen. And so now what I'm going to do is multiply the atomic weight for each element by the corresponding subscript. So I'm going to multiply hydrogen by 2 because there are 2 hydrogens. And I'm going to multiply oxygen by 1 because there's only 1 oxygen showed in this formula. Cool. And so then I'm just going to add together the results of those products. And so that will give me my molar mass. This tells me that if I have 1 mole, or 6.022 times 10 to the 23rd, water molecules, they should weigh 18.015 grams. Neat. Let's look at another example with parentheses, just to see how we're going to deal with that. So here we have aluminum nitrate. And why don't you pause the video and try calculating this dude's weight on your own? Or atomic mass, I should say. Molar mass. Molar mass, Jake. Molar mass. Anywho, pause the video. You tried that out. Let's go through it together. So we need to get the atomic weight for each of these elements. So aluminum, nitrogen, and oxygen. And next we need to multiply the atomic weight by each of the elements' corresponding subscripts. So there's only 1 aluminum, so I'll just multiply that by 1. But nitrogen, remember, if there are parentheses, we have to multiply the subscripts inside by the subscript outside. So since there's 1 nitrogen in here, I'm going to multiply that by 3. And I'm going to say there are 3 nitrogens in 1 mole, or I'm sorry, in 1 of these molecules. And I can also look at oxygen and say, all right, 3 times this 3, multiply the subscript outside by the 1 inside. So there are 9 oxygens in 1 of these. Actually, this is a formula unit because this is ionic. So only 9 oxygens in this formula unit. Well, I can multiply these together and then add together the products. So that gives me a molar mass of 212.993 grams per mole. So if I have 1 mole of aluminum nitrate, I will have 212.993 grams of aluminum nitrate. Remember, molar mass tells us what the weight of 1 mole of a particular compound or element is. Okay, let's look at this thing I talked about called the mole roadmap, because this is a very nice, useful tool for mole conversions. It's really useful if we're converting between moles or mass or volume, or we'll talk a little bit more in the next one. But volume, we can only do this when we're measuring our substances at STP, which is standard temperature and pressure, or 0 degrees Celsius and 1 atm. Because the volume of gases, or volume of substances, this is really volume of gases, this is going to change as we influence pressure, how much those gases are being squeezed, and temperature. As gases get to a higher temperature, they want to get bigger. And so we can also convert between representative particle, which you might be like, what the fork is that? Well, representative particle would mean an atom or molecule if we're talking about a covalent compound, or a formula unit if we're talking about an ionic compound. It is whatever the smallest particle of whatever thing we're talking about is. So if we're talking about pure elements, the smallest particle of a pure element is 1 atom. If we're talking about a covalent compound, the smallest building block of those covalent compounds are going to be the individual molecules. And the same thing for ionic compounds. The smallest building block of an ionic compound is that formula unit. Neat. Well, let's look at that mole roadmap. Very, very, very cool. It shows us we can convert from moles in the center back and forth to representative particles, to volume, or to mass. And this is a really nice tool because we're always going to find, or at least in the ones I provide, we're always going to find the conversion factors we want in here. and except for molar mass, which we will need to calculate. But otherwise, we're told that 1 mole is equal to the molar mass in grams. Then we're told that 1 mole is equal to 22.4 liters when we are at standard temperature and pressure. And we're also given Avogadro's number. 1 mole is equal to 6.022 times 10 to the 23rd particles. So this is our mole roadmap. It's a really nice tool. Let's talk about how we can use it. So first practice problem. How many atoms are in a 2.73 mole sample of gold? Well, what we're going to want to do is determine what conversion factor to use. Here, we are asked how many atoms. So that would be a representative particle. And we're going to be converting from moles, which we know about, to our representative particles. So we will need this as our conversion factor. And the next thing we need to do is we're going to use a dimensional analysis to perform this conversion. And it might be a multi-step conversion, but the first few we're going to look at are just single steps. So we want to change 2.73 moles into atoms because we're talking about a pure element. So I will set up my number I want to change and my X line, and I'll put the units I want to get rid of on the bottom. So we want to get rid of moles, and we want to have particles as our new units. Really, we'll rewrite atoms, but in general, I'm going to say particles until the very end of a problem. So I can cancel out the units of moles, multiply through, and this gives me 1.64 times 10 to the 24th particles, which I know is the same thing as 1.64 times 10 to the 24th gold atoms. Nifty. Let's look at another example. Why don't you pause the video on this guy and try it yourself? Sweet, you pause the video. Well, here we want to figure out how many moles we have. So we're going to be going here, and we're told volume initially, liters, so we're going to start here. So we know that the conversion factor we want to use is 1 mole equals 22.4 liters, because that relates moles and volume. So I want to set up the dimensional analysis. Well, I'm trying to change my 50 liters into moles, so I'll write 50 liters times line, which I'll put in my fraction. And this is my conversion factor. I want liters to go away, so I'll put 22.4 liters in the denominator. And I'll put my new units that I want up top, 1 mole. Well, I can see those liter units will cancel out, and I can just do 50 divided by 22.4 to give me 2.23 moles. And I know that that is 2.23 moles of CO2 gas, because we're told, hey, it's CO2 gas up here. Sick! Let's look at maybe 1 or 2 more problems. I want you to try and figure out how many liters are in a 84-gram sample of nitrogen. This one's a little bit spicier, but pause the video and see if you can handle this one yourself. Okay, sick. You pause the video. Let's talk about it together. Well, we know that there are 84 grams, so we're starting at mass, and we're asked to figure out the volume, or liters. So we're going to first have to do 2 steps here. We're going to first convert from mass to moles, and then we're going to need to convert from moles to volume. So we're going to need 2 different conversion factors. We're going to need the molar mass, and we're going to also need this 1 mole equals 22.4 liters. So I've got that one in. And my molar mass, I'm not going to go through calculating it here, but it's a pretty easy peasy one. We need to multiply our mass of nitrogen by 2 because it is N2. I'm sorry, the atomic weight of nitrogen. Okay, well, now that I have my conversion factors, I need to figure out the dimensional analysis. So I'm going to start the same way. I know my 84 grams, and so I'm going to do that times a fraction. And I want to make my grams go away and turn those into moles. That's my first step. So I'll put grams in the denominator, moles in the numerator. Up top. And so grams will cancel out with grams, and I can do this step. Boom. And so I'm just going to go ahead and set my next x bar, my next x in a fraction. And so I have units of moles now because grams got canceled, and I want to convert those moles into volume. That's what I'm trying to find. So I'll put my units of moles down below, and this is going to convert into liters because that's my final step. So I'll put my 22.4 liters at top. We can see that moles will cancel out with moles. Moles divided by moles gives us cancel out. And so now I can just multiply through. I'll do 84 divided by 28.02 times 22.4 to give me a fabulous whopping 268.6. This seems wrong, and I'm going to double check that. But this should be our final answer of 268.6 liters of nitrogen. That I'm just looking at this answer, it doesn't seem right because these 2 dudes should roughly cancel out. It should be close to 84. Anywho, that's our last problem. I'll post the thing of saying it what's right or wrong there. And that's the end of this video. I hope you feel like you understand what a mole is in the context of chemistry, are able to calculate molar mass, and more importantly, feel good about using that mole roadmap to perform conversions. Ta-ta, and have a great rest of your life.